Okay, so welcome back, everybody. So Laplace transforms are the things I wanted to talk about. We had finished, we had finished the last bit of what we wanted to do with applications of our second order theory. So this specifically was concerning spring mass systems. So we are finished with that. So then the very last thing in chapter 2 is Laplace transforms. So this topic is sort of unlike pretty much everything else in the course in terms of approach. So even like, for instance, variation of parameters, right? Variation of parameters, even though that was a different method for finding the particular solution for a non-homogeneous, variable coefficient equation, and we couldn't of course, we couldn't solve a general variable coefficient homogeneous equation. But still, like the process, like yeah, it was different, but it still satisfied this linearity business where to construct the general solution to that thing, it was homogeneous plus particular solution. So if someone gave us the homogeneous part, then we just followed this process, and it was similar in spirit, I should say, to what came before it. Right? It wasn't completely different. Even if I had to know some slightly different formula. But for Laplace transform, this is going to be a fairly distinct topic in that nothing else is really going to be like this, and this is going to require some specific techniques that don't really apply to anything else. So this is definitely like the odd man out for all of the topics in chapter 2, more or less. There's a really nice little like visual explainer for how Laplace transforms, or what's the idea behind Laplace transforms. This is on like page 2 of, so page 2, chapter 2, section 9, because that's Laplace transform. I believe it's section 9, yeah. There's a nice explainer. So what is the idea behind Laplace transforms? So the idea is that I have an initial value problem, right? An IVP. Okay, I have an IVP, and what I want is to be given IVP and then be able to solve for IVP, or solve for unknown function that solves the IVP. So solution to IVP. This is obviously what I want. Okay. So I want solution to IVP. Now, we've been doing this, and of course we can do this for, nth order linear constant coefficient. So again, we are applying this only in the case of constant coefficient, only in the case of linear equations. Again, for us, we're typically going to be doing this for second order equations, just because this is an easier thing to do. It makes the computations less tedious, and in terms of how this works, there's really no difference conceptually between applying this to a second order, third order, or seventh order equation. The process is exactly the same. Okay, so idea, I have an nth order linear constant coefficient equation. This is very important. So I do need constant coefficients here. All right, so if I'm in that case, let's say I have an IVP, nth order linear constant coefficient equation, possibly non-homogeneous, right? So if it's homogeneous, I know how to do it. So this is definitely non-homogeneous is typically what we are dealing with here. Okay, I have an IVP. I want to solve IVP. Well, that's the fundamental question, right, that we were trying to address with undetermined coefficients or key identities. Now, this will work even when the right-hand side is not in characteristic form, so this is a little bit more general than that, but anyway, this is the main thing I want. But I'm not going to go about this in the direct way. Right, my method is going to be indirect. So I'm going to take this IVP and hit it with something called a Laplace transform. So this Laplace transform, I'll call script L like this. And if I take an IVP and hit it with a Laplace transform, what that gives me is now no longer a differential equation, but an algebraic equation. And what do I mean by that? So an algebraic equation, what I mean by that is one that doesn't have any derivatives in it, one that only involves like polynomial type things and dividing by polynomial type things. So this is what I get. I take IVP, hit it with Laplace transform, I get algebraic equations. Okay, so things involving polynomials. All right, that's what I get. Now, the benefit to algebraic equations like this compared to a differential equation is, you know, that differential equations cannot be solved typically by the sort of algebraic manipulations that you would use to solve a polynomial equation, right? So the algebra tricks that you would do to solve an algebraic equation don't really work for a differential equation because it's the quantities involved depend on the derivative, and that's not really something that algebra covers, right, or can handle. So, but here we have an algebraic equation, so algebra can handle that just fine. So I do algebra to get a solution to algebraic equation. Okay. And I'm always going to be able to do that, and the process by which I do this is actually going to be pretty straightforward. It's basically going to be the exact same every time. So it's not going to require me to like really flex my algebra muscles here. This is basically going to work out to be the exact same process every single time. Okay, so this is not going to require too much on my part. So this part is really, really easy. So then I started with an IVP. I hit it with a Laplace transform. That turns it into an algebraic equation. I can solve the algebraic equation. And now somehow, of course, I want to relate the solution to this algebraic equation that I got from the IVP to the solution of the IVP itself. And it turns out in order to do that, I hit the solution to the algebraic equation with what's called the inverse Laplace transform. Which is L inverse. Okay. All right, and that takes this solution to algebraic equation, and what L inverse spits out when I hit this thing with it is the solution to the original IVP that I cared about. Okay, and so in that way I fill in this arrow here, right, by going around this way. Okay. All right, so that again may not impress you in terms of what is going on here, right? Because we haven't defined this thing, and the actual specifics of how this work are, are pretty important. So obviously, you're not going to be able to fully appreciate this until we've done a bunch of examples. But this is just I think it's important to understand this process because this is exactly what it is that's going on. So this is, anytime you see a Laplace transform problem, if you're getting confused as to exactly what's happening, this is what's happening. We're doing this process. So IVP gets hit with Laplace transform turned into algebraic equation. Algebraic equation gets solved by basic algebra, and then that solution gets hit with the inverse Laplace transform to take you back to the solution to the original thing you wanted a solution for. Okay. All right. So what is this Laplace transform thing? Well, let's start out with the definition of it. This is the definition of the Laplace transform of a function. All right, so the Laplace transform of a function f of t defined on the domain t greater than or equal to 0 is a function of the variable s that I call L of f of t of s, defined as follows: L of f of t of s is the integral from 0 to infinity of e to the minus st f of t dt. Did I lose connection for a bit? Yeah, it seems like I temporarily disconnected, so I'm not sure how much was lost. You can let me know if anything I wrote here is confusing, okay, or if there were skips or jumps, but yeah, just let me know periodically if that's an issue. So anyway, the Laplace transform of this function is this integral, where s is the variable that shows up here in this exponential argument. So this is the integral from 0 to infinity of e to the minus st f of t dt. Okay. All right. And so, if this is my definition, right? You may say, okay, well that's all well and good, but basically for every single function, I'm going to have to compute this thing using this integral. This is what I'm going to have to do. We are going to do this for a few things, and then we're going to use general properties of the Laplace transform to actually fill out the rest of our table. Okay, so these Laplace transforms, we are going to write out the Laplace transforms in a table, so that you have a table on the left-hand side, the column that contains all the functions you're taking the Laplace transform of. And on the right-hand side will be the result, taking the Laplace transform. These tables are very important. I will link the table in the chat when we're going to talk about it, so we can actually have a look at these things just line by line. The tables are important because basically in practice, when you're actually doing this Laplace transform process, it's reading the tables properly are going to be the way that you compute the Laplace transforms, not from the definition. But it is important to know the definition and know how this works, because otherwise you wouldn't even be able to get a start on this. So we are going to do some basic Laplace transforms just straight from the definition. Okay, so let's see how this goes. Let's do just a quick example here. So let f of t be equal to e to the at, right? So let's compute the Laplace transform of e to the at of s. Well, what is that according to this definition? Okay, well, this is the integral from 0 to infinity of e to the minus st times e to the at dt. Okay, so this is the integral from 0 to infinity of e to the minus s minus a times t dt. Just putting those together so we can do this integral easily, because this is just going to be an exponential thing. Okay. How do I do these improper integrals that have like one of the limits of integration or infinity, right, or something like that? Like, how are these computed? So recall from Calc 2, the way we compute these things is as a limit, right? So this is really the limit as, say, big T goes to infinity of the integral from 0 to big T of e to the minus s minus a t dt. Okay, so that's how that works. Okay, Well, now I need to actually compute this thing, because so now this makes sense, right? I have two limits of integration that are just real numbers here. So then what is the integral of this thing? Well, the integral of this thing is the limit as t goes to infinity of what? So this would be e to the minus s minus a times t over s minus a, or minus s minus a, evaluated from 0 to big T, right? Now, because we're able to divide by this s minus a, I am really going to want to do this when s is not equal to a, or else when I divide by this, I'm going to get nonsense, right? This is not going to be nice. So I really am doing this computation for s not equal to a. All right, that's just to make sure that that works. Okay. Well, let's write this out. So this is the limit as big T goes to infinity of, what do I get here? So the minus, this is minus plus, so this would be, the 0 term would have the, the e to the 0 term would be just 1 over s minus a, because it would have the plus. So this would be 1 over s minus a minus e to the minus s minus a times big T over s minus a. Well, let's take the limit of these things as big T goes to infinity. So as big T goes to infinity here, well, this term doesn't depend on big T, so this is unaffected. As big T goes to infinity of this term, what about this? What about this expression? So the denominator doesn't depend on big T at all. The numerator does. The numerator is this exponential thing. It's e to the minus s minus a times big T. Well, as big T goes to infinity, what does this thing approach? Well, it depends, right? It depends on the sign of the stuff that comes before it, right? If everything that comes before it is negative, then this would be e to the negative number times big T, as T is getting larger and larger and larger. So this would be e to the big negative number, right, which would be 0, effectively, as this thing is getting closer and closer to infinity. This is going to go to 0 if minus s minus a is negative, right? So it would be 0 in that case. If everything that comes before this is positive, however, as t goes to infinity, this expression goes to infinity. Okay, so this expression either goes to 0, right, or it goes to infinity here. So then what thing do I get in this case, right? Well, this means that I have two options, right, depending on whether this s minus a is positive or negative. So if s minus a is positive, then minus s minus a is negative, and so this thing is going to 0. But s minus a being positive, what does that mean? S minus a is positive, that means s is bigger than a. So what I get is only this first term, 1 over s minus a, if s minus a is positive or s is greater than a. And this thing is infinity if s is less than a. Now you might say, wait, isn't it minus infinity? This thing's going to infinity. But if s is less than a, s minus a is negative. So this is negative, negative, so this is positive. So it is going to positive infinity. That's not that important. The main thing is just that if s is less than a, this thing is infinite. But if s is bigger than a, I do get an actual function of s 1 over s minus a. Okay. All right. And so we can say here, oh, this Laplace transform is actually only defined when s is bigger than a. So another way of writing this work that we've done is the following. So we would say, so Laplace transform of e to the a t of s is equal to 1 over s minus a for s bigger than a. This thing is only defined when s is bigger than a. And when s is bigger than a, this Laplace transform is 1 over s minus a. Okay, so that's an example of how this is done. Let's do another example. Let's do t e to the at s. Okay, so what is this? Well, let's do the definition again. So this is the integral from 0 to infinity of e to the minus st times t e to the at dt. Again, we know we're going to run into this business. We're going to be dividing by s minus a. So we actually want s to not be equal to a off the bat. Recasting this using our definition of improper integral here, this is the limit as big T goes to infinity of the integral of 0 to big T of, let's clean this up just a little bit. So this would be T times e to the minus s minus a times t dt. All right, so that's what that would look like. Okay. So then how do we make this work here? I have t e to the so how can I deal with this? Well, let's think for a second. So what thing do I have to do here to make this work? Well, typically to deal with something like this, I would use integration by parts here. Right? That's what I would do to make this work out okay. And so what would I end up getting? Well, if I did integration by parts here, then if I let u be t and dv be e to the minus s minus a t dt, doing one integral of this thing is going to get me a minus 1 over s minus a. So that's going to show up in both terms. But then doing the second integral in the integration by parts is going to give me another minus 1 over s minus a. So if I write this as uv minus the integral of v du, du is going to be just dt because u is t. And so what I'm going to get here is the limit as big T goes to infinity of uv, which is going to be t times minus 1 over s minus a. I'm going to write it like this. Okay. Minus 1 over s minus a squared coming from that second integral. And in both cases, I can factor out, all right, both terms have a factor e to the minus s minus a times t in common. And this is evaluated from 0 to big T. Right? Okay. So let's see how this evaluation works. So this is the limit as big T goes to infinity of, let's be careful here. So evaluating at big T, I'm going to get minus big T over S minus A minus 1 over S minus A squared times e to the minus S minus A times big T. Right? Minus this whole thing with 0 plugged in. So this would be 0 over, so minus 0 over S minus A minus 1 over S minus A squared times e to the 0, right? So this would be, I'm just going to write it as e to the 0 like this. Okay. So this term goes away. This is minus minus, so this e to the 0 is just 1. Okay, so rewriting this, this is the limit as big T. Am I back? It seems like I'm disconnected yet again. So I'm not sure how much was cut out from that. Okay. So I'll see what's going on there after today. I'll call the internet provider and see what it is that's happening here, because I don't get it. Anyway, so here's this computation, right? So integration by parts here gives me this thing, evaluated from 0 to big T, doing each of these terms. So the big T term, here it is, right, minus the 0 term. So this term goes to 0. E to the 0 is just 1. So this is minus 1 over S minus A squared. So here's 1 over S minus A squared from that term. And then I have plus, this thing, minus T over S minus A minus 1 over S minus A squared times e to the minus S minus A times big T. Okay. So this whole thing goes to 0 when S minus A is positive. So that minus S minus A is negative, and so this thing is going to 0. And this whole thing blows up and goes to infinity if S minus A is negative. So we end up with a situation very similar to last time, in that this is only going to make sense when S minus A is positive. But let's write out that limit. So here's our last line of computation. So this is equal to, well, I get a split again. So this is 1 over S minus A squared if S minus A is positive or S is greater than A. And this is infinity if S is less than A. Okay, for the exact same reason. So this term is either going to infinity or it's going to 0. So if it's going to 0, then 1 over S minus A squared is all that's left. Okay. All right, so let's see. So then another way of writing this is to say that the Laplace transform of t e to the at s is equal to 1 over S minus A squared if S is greater than A. Okay. All right. Now, looking at this compared to what we got here when we just did e to the at, it may not be totally apparent here what the relationship between these things are. You might say, well, okay, it's it's the same, but I've like squared the denominator. But we'll see that actually this is our first special case of a formula or a relationship between Laplace transform of function and Laplace transform of t times function. So this multiplying by t is doing something that it may not be that apparent here what it is that's actually going on, but we'll see that later. Okay. All right. So let's do another example. All right. So this example is going to be nice because this is going to allow us to really nail down a lot more. It might not be that apparent at first that this is going to allow us to do some extra stuff, but let's do a quick Laplace transform computation of e to the ibt of s. Now, of course, I is going to be taken to be the imaginary unit. But what we're going to do here is we're actually going to just kind of do this formally. So we're just going to kind of sort of do these computations. We're just going to kind of do these computations as if these are just letters and we're just kind of symbol pushing. Okay, we're going to obey basic algebra, but we're not going to get too deeply into this. And this is going to allow us to do, you might say, I don't know how to do an integral that involves an imaginary number. But right now we're just going to do this formally, and you just have to trust me that it all works out. So what is this? Okay. So what is this? Let's do this for b not equal to 0. If b is equal to 0, then this is going to be trivial. So let's pick b not equal to 0 here. So then what do we get here? So this is going to be, I'll go ahead and write it as the limit. So this is the limit as big T goes to infinity of the integral from 0 to big T of what? This is going to be e to the minus s minus ib times t, right, dt, following the computations we did in the last couple of examples. Okay, well, let's just do this again, totally formally. What is this? This is the limit as big T goes to infinity of, this is going to be minus e to the minus s minus ib times t over s minus ib. And this is going to be evaluated from 0 to big T. Okay. So just as before, what we get when we do this evaluation is we have the limit as big T goes to infinity of 1 over s minus ib minus e to the minus s minus ib times t, times big T over s minus ib. Okay. All right. So then what do I get here? So this s I'm taking as a real parameter. This ib, if b is not 0, is some complex thing. So this minus ib to the big T term, you can take as, well, that's going to go to 1 on its own because it's going to be it's going to be going to e to the 0, which is just 1, so that's not going to affect anything. So then I need this s to be positive so that minus s is negative, right? Which would mean that the thing I'm multiplying by big T is negative, and then this thing is going to 0. Okay. Okay. Sorry, I said this thing was going to 1 before. It's going to 0. That's what I meant. So anyway, this is going to 0 so long as s is positive here. So then this is equal to the limit in the case that s is if s is greater than 0 here, this is 1 over s minus ib and this is greater than 0, and it is 0, or sorry, it is just strictly undefined if that thing doesn't disappear. Right, so if this thing doesn't disappear, there's just no value we can assign to this. So undefined for s less than 0. S equals 0 also is no good. So both of those are discarded. And so then a way of expressing this is just quickly L of e to the ibt of s is equal to 1 over s minus ib for s greater than 0. Now you might already anticipate what it is I'm going to use this for, right? So if I use Euler's formula to relate e to the ibt to sine and cosine, well, then I'm going to be able to say something, hopefully, about the Laplace transforms of sine and cosine from this fact. And that's exactly the idea. So typically, what is the way that I actually compute Laplace transforms? So here's the question. How do I typically compute Laplace transforms? So before I tell you the answer, the thing that you're probably asking now is like, well, I really hope that I don't have to use that definition every single time, because that's kind of annoying to have to compute those limits. And hey, maybe, I'm out of practice computing limits, so doing all the tricky algebra involved in computing limits is, something I'd rather not do. So the good news is that you don't have to do that typically. Typically, that's not going to be the way that we compute these things. The way that we compute these things typically is we are going to build a table of Laplace transforms for basic functions. You probably are already thinking about what some of those are, so we've already done a few of them. Right, so exponentials, t times the exponential. The exponential involves I, right, e to the ibt. Those are examples of basic functions. That one's going to give us sine and cosine, as we'll see here in a second. So there's a number of basic functions here. So we're going to build a table of Laplace transforms for basic functions, and then use general properties of the transforms. General properties of the transforms to compute them for general functions. What I mean by that is, I don't mean general function in the sense that it's just a letter, right? Like g of t is, and I don't tell you what it is. What I mean is that just like you did for derivatives, right, in Calc 1. So when you learn derivatives, right, you started out using the definition, the limit definition of derivative, and that's how you computed. But as you kept going along, right, you stopped doing that because using that definition was it was too annoying, right, to have to do that for a general function. So if maybe you had even done it, for like sine or cosine, which is already can be kind of an annoying proof to show what some of the limits or what some of derivatives of those things are. But let's say, yeah, you'd even done it for sine and cosine. Well, then you're not going to do a totally different proof for sine of 2x, right, or sine of e to the x. What you're going to do is you're going to say, I wonder what kind of pattern I can notice, right? And then you notice, say, in that instance, the chain rule, okay? And you would then, show the chain rule, and then you don't have to do, you don't have to do a different derivative proof for every single different function. You could just use the chain rule. So that's the idea. We're going to do the exact same thing for Laplace transforms. So what are some of these properties? So first big property So prop 1, you can consider that proposition 1 or property 1. The Laplace transform is linear. L is linear. What do I mean by linearity? Well, I mean that if I compute the Laplace transform of a sum of two functions, this is actually just the sum of the two Laplace transforms. Okay. What about a constant times function? Well, that's just constant times Laplace transform of function. So I have these two facts. Okay. All right. So this is what I mean by linearity. This thing splits across linear combinations, like we've kind of always meant by linearity here. So what this means is that if I knew, say, the Laplace transform of f and g, then I could immediately write down the Laplace transform of f plus g by using this fact. So this gives us a very easy way of building up Laplace transform, database, Laplace transform table. So any linear combinations, no problem, right? I can do those as I can just sum the resulting single terms and get this done. This is actually going to immediately give me Laplace transform for cosine and sine. So here's a quick fact. Cosine of bt can be written as e to the ibt plus e to the minus ibt over 2. And sine of bt can be written as e to the ibt minus e to the minus ibt over 2. Now you could write those things out explicitly to prove that. You could just trust me. You could check at least that we're not too far off base by computing, like, formally the derivative of this thing. If I compute the derivative, I get like some stuff, right, that is going to end up being b times that, but it's going to be minus, I'm going to end up with minus sine b sine bt. Similarly, if I do it here, I'm going to end up with plus, so this is going to be b cosine bt. Now, maybe you don't see that immediately that it works out like this, but you can just verify directly that this is the case. Okay, but say that we're told this is the case. I want to use this linearity to my advantage here. Okay, so let's do that. Well, then the Laplace transform of cosine of bt of s, this is equal to 1/2 times the Laplace transform of e to the ibt. Notice I've already used linearity there by factoring out the 1/2, plus 1/2 times Laplace transform of e to the minus ibt of s. Okay, but then we computed what this thing is, right? Laplace transform of e to the ibt is 1 over s minus ib. So this is 1/2 times 1 over s minus ib plus 1/2 times 1 over s plus ib, because of that minus sign. But remember how we actually compute 1 over a complex number. So we use the complex conjugate. Right, we use the complex conjugate here. So this is 1/2 times this thing is s plus IB over the modulus of this thing squared, which is s squared plus b squared, plus 1/2 times the conjugate here is s minus IB over s squared plus b squared. So the 1/2 plus IB over s squared plus b squared cancels out with 1/2 minus IB s squared plus b squared. And I'm left with 1/2 s over s squared plus b squared plus 1/2 s over s squared plus b squared. So this is s over s squared plus b squared. Okay. Let's do similarly the Laplace transform of sine of bt of s. What is that? Oh, sorry, I rewrote. I didn't write this properly. This is not a 2 here. This has to be a 2i for this to work. Okay, so if you were confused trying to actually compute the derivative of this to make sure it lined up, there's an extra I here. This doesn't work. Yeah, so that's what I get for doing it in my head. Was screwing up and forgetting that. So anyway, this is yeah, this has to be an I or this doesn't work. Okay. So and you might say, well, does that screw everything up here? No, the constant before this is more like a formal thing. So when I go back to my linearity property, here this c can be a scalar or constant in the sense that it can be a real or complex number here. This is still going to work out fine. If you don't believe that, again, you could just kind of treat this formally and symbol push with the definition to show that, oh yeah, it doesn't actually matter. Okay, so this is a Laplace transform of sine of bt of s. What is this? So according to this relationship, this again would be 1 over 2i times Laplace transform of e to the ibt of s plus 1 over 2i times the Laplace transform. And this shouldn't be a plus, this should actually be a minus. So I'll go ahead and pull the minus out. So here, let's make this a, yeah, that should be a minus. So minus 1 over 2i Laplace transform of e to the minus ibt of s. This is just so that I don't have a minus inside that I have to take out here. Okay, so what do I get here? This is 1 over 2i times Laplace transform of this, as we saw before. This is s, or sorry, this is 1, I'll write it like this. This is 1 over s minus ib, right? Minus 1 over 2i times 1 over s plus ib. So then let's just keep these 1 over 2i's as they are. So this would be 1 over 2i times this, again, inverting this, this would be its conjugate over s squared plus b squared, which is the modulus squared. This is 1 over 2i times s plus ib over s squared plus b squared minus 1 over 2i times s minus ib over s squared plus b squared. And let's think for a second here. So now the term that's going to get canceled here is, I'm going to have 1 over 2i s over s squared plus b squared minus 1 over 2i s over s squared plus b squared. So the s term cancels. And so what I get is 1 over 2i times ib over s squared plus b squared. So the i's cancel and I get 1/2 b over s squared plus b squared minus ib over 2i over s squared plus b squared. So the i's cancel and I get plus 1/2 b over s squared plus b squared. So I get 1/2 b over s squared plus b squared plus 1/2 b over s squared plus b squared. So what I get here is actually b over s squared plus b squared. Which did not seem likely that we would go in this direction. Okay, from maybe this or this, which looks like a nastier thing, but this is exactly what we get. So let's rewrite this in a nice and simplified fashion. Thus, the Laplace transform of cosine of bt of s is equal to s over s squared plus b, s squared plus b squared, and Laplace transform of sine of bt of s is equal to b over s squared plus b squared. Aha, so now we're getting somewhere. Okay, now we are happier here. Okay, and this was true. We had to assume that s was positive here for s greater than 0. Okay. All right. So if we were trying to do this directly from the definitions, we could have done it, but it would have been pretty rough. It would have involved some nasty computations involving cyclic integration by parts. It can be done. It's not impossible or anything, but this is a nicer way of doing it. And this also hints to what it is we're actually going to be doing, which is using these properties. Let's do another expression here that is actually hinted at by this fact that we used this expression, these relationships between cosine and sine, and e to the IBT and e to the minus IBT. So we have these weird relationships. You've probably never seen these before, these ways of writing cosine and sine, because in previous classes cosine and sine were simple enough and it wouldn't have been nice to put them in this form. But for us, it was nice to put them in this form because we'd already computed the Laplace transform of these things, right? Even though they had the imaginary unit in them. But this hints at something that we can do here. What if I get rid of the I? What if I get rid of the I here? What functions do I get? What do I mean get rid of the I? I mean, what if I write the function e to the bt plus e to the minus bt over 2, and I write the function here, getting rid of the I, e to the bt minus e to the minus bt over 2. Again, I'm getting rid of the I. What are these? You might not have seen these before. These are what are called the hyperbolic trig functions. Hyperbolic cosine, or cosh. So this is cosh of bt. And this is sinh of bt. So this is hyperbolic cosine. Like I said, that is called cosh. And this is hyperbolic sine. These are examples of what are called hyperbolic trig functions. Now, unfortunately, although I would really love to, it is hard to explain why these things are important, where they come up, but I'll just give you the quick example. So, in the Euclidean plane, when you're doing Euclidean geometry, you may remember, right, but from high school, you have some laws coming from trigonometry, the law of sines, the law of cosines. Okay, you might remember those names at least. You don't have to remember them off the top of your head, but just those might ring a bell. Okay, Well, you might not know about this, but there are examples of non-Euclidean geometries, um, and they can be modeled on a plane as well, although it's called the hyperbolic plane. Okay, this is an example of one of these non-Euclidean geometries. And in the hyperbolic plane, you also have a law of sines and law of cosines. But instead of the normal cosine and sine showing up, the functions that show up instead are cosh and sinh, the hyperbolic cosine and the hyperbolic sine. These really play the same role as sine and cosine. Now, if you don't believe me, let's just check something really quickly. Right, so I'm going to use just cosh of t, so b is 1 here. So what is the derivative of cosh of t? All right, to show you that this behaves like sine and cosine, derivative of cosh of t is e to the t minus, again, I'm letting b equal 1 here. So this would be e to the t minus e to the minus t over 2. But that's sinh of t. What's the derivative of sinh of t? Sinh of bt is this, so sinh of t is e to the t minus e to the minus t. So it's minus minus, so it's plus, so it's e to the t plus e to the minus t over 2. But that's cosh t. So actually it's even nicer. You don't have to remember which direction gives you a minus sign here. All right, so that's nice. Okay, so here's derivative of cosh t is sinh t, derivative of sinh t is cosh t. Let's check some other similarities. What's cosh of 0? This would be e to the 0 plus e to the 0 over 2. That's 1 plus 1 over 2, which is 1. What is sinh 0? Well, it's e to the 0 minus e to the 0 over 2. So this is 1 minus 1 over 2, which is 0. Okay. Now, one more thing, just because I can't resist myself when talking about this thing. You may have come across something in quest. Well, let me see if do I have something that kind of illustrates this. All these chords that I have are kind of too rigid to illustrate what it is that's going on here. Do I have a chain? Let's see here. Do I have a chain or a string of some kind? Yeah, these chords are a little too rigid. Let's see here. Well, I will find a string somehow. This is an important conceptual thing going on here, right? Again, all these are a little bit too rigid, but I'll use them anyway. Okay. So, if I take a piece of string like this, now again, this is a little rigid. This is a chord to a keyboard, so this is a little rigid. But if I take a string like this and I fix both ends and I just let it hang, right? So that the only force acting on it is like gravity, right? So it's some weighted chain or something, and I just let it hang from both ends like that. Okay. All right. So then what shape does it make? Well, you might be tempted to say it's like some parabolic thing, right? But of course, depending on the chain, this thing could look more like that. That's not really a parabola. You might say, oh, it's like a fat parabola, right? It could also look more like this. And you say, okay, that still looks kind of like a parabola. But remember, parabolas have a very specific definition. And the original definition of parabola as a conic section means there's relationships that have to be satisfied, between certain things, certain points on the parabola. And if that isn't satisfied, it's not technically a parabola, even if it looks like it. So what that image looks like is this. Sorry, I did a bad job there, but it looks something like that, we'll say. This shape, this curve that is traced out by fixing some weighted chain to two ends and just letting gravity shape this thing. This shape is called catenary, or catenary if you're British. So the catenary is what this is called. What is the catenary? This is the graph of cosh t. Now, not every catenary is a graph of cosh t. It might be the graph of cosh of 10t or something, or cosh of 10t minus 7. It could be some shifted catenary, but the idea is that the basic catenary shape is contained in this hyperbolic cosine function. All right. Okay, that little aspect is not going to be too important for us in this class, but in case you were wondering where it came from, that's an example. Okay. All right. So, moving on. What now? Well, I wanted to use this fact and the linearity to compute the Laplace transform of these two things. So let's do that really quickly. So I'm going to use this for cosh and sinh. So what is the Laplace transform of cosh of, we'll just do cosh of bt here. So we'll do the general thing. So cosh of bt of s, well, according to this is 1/2 times the Laplace transform of e to the bt of s plus 1/2 times the Laplace transform of e to the minus bt of s, which very quickly, what is this? This is 1/2. Right. This is 1/2 1 over s minus b, right? Plus 1/2 times 1 over s plus b. Okay. Which, if I do the algebra here, right, I multiply these two things, I get, this is how difference of squares factors. And so what I get if I combine these two things is 1/2, right? This is 1/2 s plus b over s squared minus b squared, plus 1/2 over s minus b times s squared minus b squared. The b's cancel, and what I get here is s over s squared minus b squared. Okay. And Laplace transform of sinh of t, I won't go through all of this, but it's very simple. Again, it looks like I cut out, so I apologize for that. I'm not sure how long I was cut out for, but anyway, this is all I wrote in that time, only for a couple of seconds. Well, that's really, really good. Hopefully it was like that for all of those, because like I said, it on my end, I just got some giant warning flashing thing, and it acted like I'd been frozen for 5 minutes. So anyway, so hopefully not too much is being missed out. I have to go back in YouTube Studio and edit it and look and see how bad it was. But hopefully, like I said, I'm going to call internet folks and make sure that it's not doing this tomorrow, hopefully. Okay, so anyway, this is the Laplace transform of sinh. Now, this is kind of getting us towards all of the full list of properties that we're going to use. The next property, we'll call it prop 2 of Laplace transforms, is if, let's say we have the Laplace transform of f of s, and this thing exists for all, we'll say, s greater than a. Okay, and if a is any real number, so if a is any real number, then a is just some real number, then the Laplace transform of e to the at times f of t of s, so I can multiply a function by e to the at. What is that? That's actually just the Laplace transform of f that has been shifted by a. Now, you can remember this boxed relationship. There's nothing wrong with remembering this. Conceptually, a thing that makes this kind of easier to remember is the following, which is to say multiplying by e to the at shifts the Laplace transform by a. So you have a function, you take that function and you multiply by e to the at. If you take the Laplace transform of that multiplied thing, that is like you took the Laplace transform of f and then just shifted it. So the reason that this is important and gets you out of doing some amount of work is that you now no longer have to factor this e to the at into like whatever kind of, whatever kind of expression this becomes. You could actually just ignore that, find the Laplace transform of f, which I'm assuming exists here, find the Laplace transform of f, and then shift that thing just by, instead of having s here, it would be s minus a. So that is really, really nice, and we're going to use that fact a lot. Going forwards and backwards. Now, I haven't talked about going backwards yet, but you'll see that's not a big deal. So this then gives you a ton of new Laplace transforms. So this fact gives us many new Laplace transforms. Okay, so let's just do some of them, right? So for instance, if I wanted to do the Laplace transform of, instead of just e to the ibt, what if I wanted to do e to any complex number, e to the a plus ibt, right? That's e to the a times e to the ibt, right? So that's e to the at times e to the ibt is what this is. So then I should just replace s with s minus a. Well, what is this? Let's go all the way back here. Where are we going? Here we go. So here's my Laplace transform of e to the ibt. The only difference between e to the ibt and e to the a plus ibt is I'm multiplying by e to the at, right? So then I take this and I replace it with s minus a. So I replace s with s minus a. So this is 1 over s minus a minus ib. And that's it. What about the Laplace transform of e to the at times cosine of bt of s? Well, Laplace transform of cosine of bt is s over s squared plus b squared. So every s gets replaced with s minus a. So this is s minus a over s minus a squared plus b squared. Okay, similarly, Laplace transform of e to the at sine bt of s is what? Well, Laplace transform of sine of bt is b over s squared plus b squared. So this is b over s minus a squared plus b squared. Okay. What about Laplace transform of e to the at times cosh bt of s? Sinh will be similar, so we'll just do this. Well, remember this was s over, so this was s, I'll bring this up. Laplace transform of cosh was s over s squared minus b squared. So this would be s minus a over s minus a squared minus b squared. All right, and similar for sinh. I'm not going to rewrite that. Okay. Now I want to do an opposite thing. It will be clear why I'm doing this. I'm building in the inverse Laplace transform information doing it this way. So property 2 told me that multiplying by e to the at shifted my Laplace transform by a. It was a translation. by A. So this shifting Laplace transform by A, this is translation by A. Okay. Now, before I can talk about this next property, I want to discuss what's called the Heaviside function. So what's the Heaviside function? Well, this is also called the unit step function. You may have seen this previously. This is the function. One way of thinking about it is it's like a switch, okay? And the way that it is normalized here is that it's a switch function that is off or 0, right? So I'm doing that to indicate it's not actually zigzagging, right? It's just off until 0. And then at 0 it turns on, which indicates that it takes on the constant value 1. So it is a function that is off, taking on constant value 0 up until 0, and then at 0 it switches on and takes on the constant value of 1. So in our notes, the Heaviside function is denoted by u of t. This is for a unit step function. U of t is the piecewise constant function that is 1 if, so for t greater than or equal to 0, and 0 else, right? So for t less than 0. So it's off until 0. At 0 it turns on, right? Off is 0, on is 1. This is my Heaviside function. Okay. Now, see what the Heaviside function does to a function if I multiply by it, right? So if I take the Heaviside function and any function, so u of t times f of t, if f of t is some function that this such that this thing's actually defined, so we'll say that f is a function that is at least defined for t greater than or equal to 0. What do I get here? Well, when t is greater than or equal to 0, I just get f of t, right? But before t is 0, I get 0 because I'm multiplying by a thing that is 0. So this is 0 for t less than 0. And so here's a primary use of the Heaviside function. If I multiply it by some function f of t, whatever it is, this is the resulting thing is basically a function that is off until 0, and then at 0 it turns on, and it has that function's values up to that point. So what would this look like, right? So maybe f of t looks like this. Maybe f of t looks like this. Okay, maybe that's what f of t looks like. But then u of t times f of t is going to look like what? Well, all this part of f is going to get zeroed out. So it's just going to be 0. And then at 1, this thing turns on, so just this piece, right, turns on. So this is what u of t, f of t would look like. It would be 0, and then it would turn on at 0, and from that point on, it would have the same functional values as f. Okay. Okay. Now, let's look at something else. Let's see be some positive number. And let's look at u of t minus c times f of t minus c. What is this? This is a shifted multiplication of Heaviside function times function. And what I get is this function agrees, so this agrees with the functional values of t minus c when t minus c is greater than or equal to 0, and it's 0 for t minus c less than 0. Let's rewrite this though, right? So all I did between here and here is replace t with t minus c. So this is, I did nothing going from here to here. But let's actually see what it is that's going on here. This is, the first piece is f of t minus c. That's for t minus c is greater than or equal to 0, but another way of saying that is for t greater than or equal to c, and 0 for t minus c less than 0 or t strictly less than c. What did I do here? What's the difference between this, and now I'm going to write, see if I can fit this in here. This, and u of t minus c, f of t minus c. What has happened here? Well, now, instead of turning this picture on at 0, I'm turning it on at c. So maybe here is c, or yeah, maybe here is c. So instead of getting this picture, what I get is this is 0 until c, and then it turns on. Right? From that piece on, like if maybe here is c, just this piece is turning on, that and everything after it. Okay. All right. So u of t minus c times f of t minus c turns on f starting at c. Okay. So this is really a shift by c. Okay, this is shifts to the right, right? So this is a shift by c. Okay. Okay, so this has shifted f of t by c. That's all this has done here. Okay. Okay. So here is the statement that I want to make that kind of brings all this together. We'll call this property 3, or proposition 3, however you want to think about it. Prop 3, if the Laplace transform of f(s) exists for all s greater than, say, alpha here, and let's let c be any constant, so c greater than 0, then the Laplace transform of u of t minus c, f of t minus c of s exists for the same, on the exact same domain, and we can actually say explicitly Laplace transform of u of t minus c times f of t minus c of s is equal to e to the minus cs times the Laplace transform of f of s. Now, why did I go through all the hassle to write all this down? Other than the fact that this is actually going to come up for us. This is something that we're going to have to do, okay, or deal with. So here we go. You can, of course, remember this, and you should remember this form. But what's important is to actually look at this expression and say, okay, conceptually, what is it that's going on here? This is a shift by c, right? And this translates into a multiplication by e to the minus cs, right? So this is kind of the way of thinking about it here, right? So shift or translation by c gives us multiplication by e to the minus cs. You don't have to necessarily think about it like that. It's that shift by c in the Laplace transform gives multiplication of the Laplace transform by an exponential, look at what happened going in the other direction, right? In the other direction, multiplication by e in the Laplace transform led to a shift, okay, or a translation by a. So there's like this duality kind of, right? So it's translation in this sense leads to multiplication by exponential. Multiplication by exponential leads to translation in this sense. Okay, so there's a very good analogy between these things. This is just kind of trying to keep all of these things separate in your head. So tomorrow we will see the last of these properties that we're going to use, and then we will do a ton of examples. Okay, so tomorrow that would be lecture. Today was what, lecture 15? So tomorrow's lecture 16. We will do many examples of these problems. Okay, so you don't want to miss that. You'll definitely want to see that. Our main, kind of the main flex for Laplace transform stuff is there's going to be one specific instance where we can use Laplace transforms that we really can't use anything else in a way that's not completely ridiculous. So I won't spoil the fun. I will wait until we get there so that you can actually see what it is I'm talking about. But it's pretty cool. So anyway, that's the deal. So I will see you all tomorrow. Remember your oh, I guess your exam was actually already due. I think, right? It was due yesterday. Anyway, okay. So I was just going to remind you, but that's fine. I'll post some new homework soon, so you can be looking for that. I'll make an announcement later. But anyway, I will see you all very soon. Since our exam is over, we'll be able to discuss the answers. Yes. So I'm going to have some office hours this week. So not tomorrow. I'll probably do it on Thursday. So I'll post an announcement and link to all that stuff, and you can ask any questions you have about the exam. So yeah, if you have any questions about the exam, just go ahead and ask them. Then also, like I said, I'm going to post more homework, and your first MATLAB project I'm going to go ahead and post. It'll be due in like a week. After it's due, I'll post your second MATLAB project. It will be due, by like the last day of the semester or something like that, or maybe in like a week and a half after that, which would put it close anyway. So yeah, that's the deal. I guess we've marked like the official halfway point of the course, right? So this is to be expected. We're going to have things ramping up, but I'll let you know about all that stuff later. You haven't missed anything, so I'll post any more homework and MATLAB projects a bit later. So anyway, so that's that. So yeah, just ask me if you have questions about the exam. Then ask me later. Don't discuss it with other students quite yet. Just wait until office hours, and then we'll freely talk about it. All right. So anyway, I will see you all then.